All right, guys, here we go with a new chapter for you guys. This is going to be Circular Motion, Chapter 7. We're going to do a couple things. We're not doing that much trig, but you need to know a little bit about angles, and I know you have the math, so you guys can take care of it. So let's talk about what is circular motion. Basically, it's any object moving in a circle or an arc. So if somebody's going around a racetrack, that car is around that curve. That is circular motion because it's going in an arc. Now, you think about having a weight on a string, you swing it above your head, swinging it horizontally or circular. You got this circle and you're keeping it there, and the car or the object that's moving in the circle has an acceleration because it's changing its velocity. The velocity is changing, not the speed per se, but actual direction, and that gives us an acceleration, and that acceleration is called centripetal acceleration. And what is due to that is this something called tangential speed, which is the speed of the object that's tangent to the circle. So what we mean by that, let's go to the next slide and let's see. Pen color, let's go with, let's see. Right, so what do I mean? So what we have is something going in a circle. Wow, what a circle. And if you take a look at this point, there's an instantaneous velocity that goes this way. This is the speed, tangential speed. Here's the tangential speed at this point. This looks bad in this. And so this is what I mean by tangential speed. And the centripetal acceleration is basically acceleration as this changes. And so there's an equation for that. Now I'm going to change this pen color before everybody yells at me. Yellow. Let's see how this works. Here's a tangential velocity. This is in meters per second. The radius has to be in meters, and the acceleration is meters per second squared. So, and look, the centripetal acceleration is basically the velocity, the tangential velocity squared divided by the radius of the circle or arc. So if we have an arc, here's my arc. It's the radius of this arc is that we're interested in. Here's the race car coming in, goes around the curve, and comes out. And this is the arc from this point to this point that has this radius. All right, hopefully that is understandable. I got some other figures to talk to you about. So when we look at the change in velocity, here's our change. Ooh, that's A is point A. This is a point our first measurement, initial velocity. Point B is where we finish measuring, and this is final velocity. So when we look at this, you notice that this arrow is going this way, and this arrow is going this way. And so if we look at final minus initial, and this is what this next slide does, here's delta V is our final, is final minus initial. You look at that change in velocity, the magnitude stays the same, but the direction is heading towards the center. So the direction of the velocity change is towards the center of the circle. So this is always true. So we got this thing coming down, we got this difference, and it's always towards the center. Always. So this is what the change of velocity does. So when we look at this change in velocity and so forth, we got to realize that's what's making that change in the velocity, the acceleration, is actually something called centripetal force. And that's the force acting on an object. And you got the force of the string and the force of gravitational analysis. And if we look at something like this, here's the force, here's the velocity going out, and this force, the net force, the centripetal force, is keeping this thing towards us. This is the force that's heading into us. And force is equal to mass times acceleration. And for this centripetal force, we're looking at acceleration is going to be Vt squared over r. That's the centripetal acceleration, so the force is actually going to be mass times this divided by r. And that's one of the equations you're going to use. And I'll explain more of this when we hit to our example videos. Now what we have is, when we have a free fall object that's going to be moving. So what we have is we have our planet, and we got something up here, and we shoot it off in a horizontal direction. If it's got a little bit of velocity, it's going to crash to Earth. It's going to gain a little bit away, and then going to crash. And then as we increase the speed, it's going over more, and then it's going to be up to a speed that it almost breaks the gravitational pull, but it's constantly falling. It's falling away from the rotation of the planet. So it wants to fall down, but the planet is moving as well, and it's spinning, and it's got this curvature, and it ends up going to go rotating in a circular motion. And this is what we mean by free fall. The force over and force down are canceling each other, the force going this way, and basically we're weightless. This is what we mean by free-falling objects. Now when we look at gravity, this is a field force. So gravity is what we call field force. Meaning that it doesn't have to be next to each other in order to attract things. And it has an attraction. So this field force has an attractive force. It doesn't repel anything, it just attracts things. And this is what we need to focus on, is what the force attraction. Now, Newton figured out the equation for gravitational force, and the gravitational force is equal to this constant g, the gravitational constant. M1 and M2 are two masses. So we've got M1, M2 is away from distance away from it, and the total gravitational force is equal to the distance between the two. Now, this is the total force in between these two. And we know that one's one way, one's from the other. We look at from the point of respective forces, point of view. And I want to point out that for gravitational pull, the acceleration of gravity is equal to the force divided by the mass of the object that's falling down. And look what happens when we input that into this equation. Gravitational constant times the mass of the object times mass of the Earth divided by mass of the object in r squared e, which is the radius of the Earth. the masses cancel, and we have this equation, and you notice that the mass of the object is nowhere present. So the mass of the Earth is actually doing the pulling us down. Our masses had nothing to do with the gravitational constant. So this is fast, this is dirty. If you have any questions, please leave something at the end of the slide. Thank you guys, and have a nice day.